Hello, Chem 213 students, and welcome back for our last lecture of this week. This is going to be about the remaining nucleophiles that will be involved in carbonyl nucleophilic additions. Previously, we talked about carbonyl nucleophilic additions for ketones and aldehydes with nucleophiles that have the oxygen atom, the nitrogen atom, and the sulfur atom, and the hydride ion. Now we're going to start to talk about carbon nucleophiles. When I finished off, we were talking about the carbon nucleophile that we're already been introduced to. It's the Grignard reagent. So the Grignard reagent involved a carbanion composed here of, in this case, with this example, it'd be CH3 with a minus, and does a nucleophilic attack on the carbonyl. And ultimately, what is produced is a carbon that is attached to both another carbon and bears a hydroxyl group. And remember, these nucleophilic attack, this has been a common thread throughout this chapter. When they produce a carbon chiral center, that carbon will have a mixed R and S configuration, or you have a racemic product because of the flat nature of the carbonyl. So the nucleophile can attack in equal likelihood from the front of this carbonyl or from the back. Recall that the Grignard mechanism is quite simple. We simply have the attack of the carbanion and the carbonyl, a resonance arrow to show the lone pair now in the oxygen bearing 3 lone pairs, and one bond giving it a negative formal charge, ultimately protonated by acid after in a second step of the Grignard reaction. Remember, you can't have acid in the first step because it will protonate the Grignard reagent itself, which would be quite basic, being a carbon atom. Next, we're going to move on to new carbon-containing nucleophiles that we have not seen in previous chapters. One here being the cyanide ion, being the nucleophile attacking the carbonyl. So this is going to result in a cyanohydrin. This is going to be a reaction that's similar in mechanism to what we just saw. The reaction works under slightly basic conditions, and this is, or we can add a little cyanide. You want it slightly basic because when you add a little cyanide, the cyanide's going to be catalytic, meaning you only need a little bit to get things started, and it's going to do a nucleophilic attack here on the carbon, which remember bears this partially positive charge. The other way we can look at it, I think it's a little bit easier to see it when you just have when you just indicate here the positive charge. Here we have a pi bond between two atoms of differing electronegativity, which gives us the oxygen with the single bond bearing the negative charge, leaving the carbon here with 3 bonds and no lone pairs, having a positive formal charge. So again, that's the main theme of this chapter. I just wanted to bring it up one last time on this third lecture to make sure you're constantly thinking of that negative attacking the positive. That's what should drive your thinking. But there's also this same resonance arrow that I've shown here, indicating the movement of those pi electrons to be on the oxygen bond, and then a subsequent protonation by the acid. So the mechanism is the same as the Grignard. Here's that same mechanism being drawn. You have the attack, putting a third pair of electrons on the oxygen for the -1 formal charge, and then a proton transfer from the hydrocyanic acid, grabbing the proton here, both these electrons here being left behind, and ultimately producing this product. The cyanohydrin. Now with this, notice that the cyanide on here is catalytic. You only need a little bit to react at any one time because it's immediately regenerated upon the protonation of the oxygen. So usually it's just a weakly basic environment with some cyanide ions added in so that they won't all be protonated. But there's also some hydrocyanic acid in here as well. So achieve the basic conditions. Generally, you have an equilibrium between the hydrocyanic acid and the cyanide ions themselves. This equilibrium going on here. And so you introduce a little bit of both, and you'll have as long as it's not too acidic, as long as you have a good mixture of the weak acid and its conjugate base, you'll have a decent amount of both. And the cyanide ions will not be consumed completely. They will just be used to initiate the reaction and then be reprotonated to give you back the hydrocyanic acid. So because of this weak acid equilibrium, you'll have a significant amount of both. Now, when this reaction occurs, it does favor the formation of the cyanohydrin. You can see here acetone undergoing this reaction produces about 78% yield of the cyanohydrin, leaving only about 22% of the reactants remaining. It's even more, you'll get even a greater proportion of products here, 88% yield here for this benzylic, for the aldehyde here, this benzylic aldehyde. And you'll get the cyanohydrin. Again, you're going to get a racemic mixture, so here that doesn't matter because this carbon is not chiral, bearing two methyl groups. But here this carbon is chiral, and so it's important to note, like all these mechanisms, since the nucleophile is attacking on a sp2 hybridized trigonal planar carbon, it can equally likely attack from either side and give a racemic mixture of products. Now, one reason why you might want to install this group is, number one, it adds an additional carbon atom. So remember, we don't have too many synthetic ways to add additional carbon atoms now. We've got the Grignard reaction, we've got the alkylnide ions, the deprotonated carbon-carbon triple bonds, which can serve as nucleophiles to add carbon atoms. But this is the third way that we have recognized here of adding additional carbon atoms. Through the installation of the cyano group here. And, well, I guess it's the fourth because we previously saw, some other, well, no, this is the second. Sorry, I'm going back here. Yeah, so this is our third way of doing this. Sorry, waffling there a little bit. But going back here, if we add this additional carbon atom and we want to reduce the product so that the nitrogen here is an amine, we can use a mild reducing agent such as lithium aluminum hydride and then water afterwards to make sure the amine is protonated here. And here we will get a primary amine with an additional carbon atom added. Notice we've added a carbon atom here. We still have the alcohol group, but we have the amine one carbon away from the carbon attached to the alcohol group. Likewise, we can also oxidize this under acidic conditions here to produce a carboxylic acid, and that would result in a racemic mixture. Again, both of these will result in racemic mixtures because they involve the attack of a nucleophile on the carbon atom here. Now, another way of installing additional carbon atoms in a way that will produce a carbon-carbon double bond is the so-called Wittig reaction. So the Wittig reaction is extremely important in organic chemistry, just like Grignard reactions. It's because you're adding additional carbon atoms to the skeleton, and you can potentially add more than one. So you'll have a ketone or an aldehyde basically converted into a carbon-carbon double bond. Effectively, that's what's going on. This oxygen is replaced with a carbon atom, and depending on the type of Wittig reagent that you use, you can have either just one carbon attached here or multiple carbons attached, but either way, you're adding additional carbon atoms to the skeleton. This is one of these few ways that we have to do that. And we get this new carbon-carbon double bond as well, and we know carbon-carbon double bonds are quite reactive, so we can go on and do other things with those carbon-carbon double bonds as well. The Wittig reagent is called a phosphorus ylide ion. It's actually, I'm sorry, this is actually called Wittig, I guess, in German with a V, but I might say Wittig just because I'm reading it, but technically it's pronounced Wittig. But anyway, the result here is something that's like a carbanion with the phosphorus bearing a positive formal charge here. We're not accustomed to calculating formal charges on phosphorus as often, but remember, if we're calculating formal charges, we can pretend like the atom gets all of its electrons in lone pairs, but only one of the two electrons in a bond, and then we take its normal number of valence electrons, which for phosphorus would be 5 valence electrons, and we subtract out how many electrons it's getting in this accounting measure, which would be 4. And so that would leave us with a +1, and that gives us a +1 formal charge there. For the carbon, we could do the same method, but by now I'm sure you know that a carbon with 3 bonds and 1 lone pair has a -1 formal charge. You can write a resonance structure for this in which you make a double bond between the carbon and the phosphorus here, and that gives the phosphorus 5 dots now, giving it 0 formal charge. So there's 5 dots in this little circle here, giving it 0 formal charge. The carbon is also making 4 bonds with no lone pairs, giving it 0 formal charge. However, in reality, this is actually more reflective of the left one here is more reflective of the actual distribution of the electron density. And it also is more apparent that it's going to be the carbon, the atom, that will be acting as a nucleophile and doing the nucleophilic attack on the carbonyl. So in terms of the formation of the Wittig reagent here, the Wittig reagent proceeds through a cyclic type mechanism where, or the usage rather of the Wittig reagent here, now with this carbanion here, is the attack of the carbanion in the Wittig reagent here on the positively formal charged carbon. And again, we have a resonance arrow here, but we would have a resonance arrow, but instead here we have a kind of cyclic reaction. It's like a 2-2 cycloaddition. And so these pi electrons instead form a bond to the phosphorus. So instead of having that second resonance arrow that we've seen again and again, instead we're going to have those pi electrons going into the formation of a sigma bond to the phosphorus, forming a so-called oxaphosphatane intermediate. And then finally we have a fragmentation of this, and ultimately these electrons here between the carbon and the phosphorus, this sigma bond breaks, and these electrons go into making a pi bond between the 2 carbon atoms, giving us our carbon-carbon double bond. And then we have the cleavage of the oxygen-carbon bond, and the whole remaining, and that leaves a double bond between the oxygen and phosphorus. And so this remaining reactant is taken, or product here is taken out, and we get our carbon-carbon double bond formed by this Wittig reaction. And it's saying this particular product here, if we take a look at it, we get a phosphorus oxygen double bond, quite a stable bond here. This product also, because of the phenyl groups and the double bond here, has exceptional resonance to it, and so it's particularly stable. And so the formation of this product really drives this reaction forward, and you get quite a large yield for this. Now, where does this Wittig reagent come from? Well, you start with the triphenyl phosphorus here, and that phosphorus has 3 bonds and 1 lone pair, just like you would expect for a nitrogen or a phosphorus atom. And if you combine that with an alkyl halide, in this case, the lone pair on the phosphorus atoms will behave as a nucleophile and will perform an SN2 reaction. And so we'll have the simultaneous nucleophilic attack on a carbon attached to the bromine here. This polar bond means that the carbon has a partial positive charge. The bromide has a partial negative charge. And so we have the simultaneous leaving of the bromide group, and this is a standard SN2 reaction. Now, where does this triphenyl phosphorus come from? Well, we can have, if we want to have a larger number of carbon atoms, we could also react this triphenyl phosphorus with a carbon atom, and then ultimately subject that to another reaction with a very strong base that will deprotonate this carbon atom and ultimately give us the Wittig reagent. And so we've got this pathway here, which is the treatment of the alkyl halide with the triphenyl phosphorus here, which performs an SN2 reaction and produces this salt with the bromide ion leaving here and ultimately producing this positively formal charged phosphorus because it has 4 atoms and no lone pairs. So this is like a nitrogen atom with four bonds and no lone pairs. It has a positive formal charge to it. This carbon here has no formal charge because it has 4 bonds and no lone pairs. We then have an attack here by the or deprotonation here by this strong base, the lithium butylnide here, and reagent, and then we have after that deprotonation, we have a carbon here that these 2 electrons here are left on the carbon, giving us 3 bonds and 1 lone pair, and thus a negative formal charge. And at that point, we have the Wittig reagent, and we can draw the resonance structure here, where we show the lone pair electrons here instead as a carbon phosphorus double bond, leaving the phosphorus with 5 bonds, thus giving it no formal charge as we had discussed, and the carbon here making 4 bonds with no lone pairs, thus giving it no formal charge. And but again, this is the essentially the the more accurate representation here of the electron distribution. And so we have this is the way the Wittig reagent is formed. Now, the Wittig reaction is useful because it gives us a carbon-carbon double bond, and we know from Chapter 8 in Chem 212 all of the reactions the addition reactions that carbon-carbon double bonds can undergo. So this makes it very synthetically useful. It's important to note that the Wittig reaction will give you the Z stereoisomer in the case where you have a Wittig reagent without any electron withdrawing groups. And so here we have a Wittig reagent in which there's not just 1 carbon atom attached here, there's actually 2. So we have 2 carbon atoms attached. And so now this is going to be, when we add this carbon atom here, we're going to get an asymmetrical product because we have 2 different groups attached to the carbon atom that's double bonded to the phosphorus. And so when the reaction proceeds, and we get the again, remember, we can show this as its resonance structure here, which is a little bit more truly representative of this reagent, where now the lone pair is shown on the carbon, giving it a negative formal charge, and the phosphorus is making 4 bonds with no lone pairs, giving it a positive formal charge. And that then undergoes the nucleophilic attack on our carbonyl like that. And remember that there's also, it's hard to draw here, but also these pi electrons here go into forming that that 2-2 cycle addition, and then the subsequent, going back to the mechanism here, the subsequent ejection of this triphenylphosphine group and the formation of the carbon-carbon double bond. But note here that we have 2 potential stereoisomers. If these 2 were switched, we'd call that the E. Now that the larger group, so if we rank these groups here, the carbon has higher molar mass than the hydrogen, so it's priority 1 versus hydrogen priority 2. The carbon here has higher molar mass than the hydrogen, and so it gets priority 1. And since the priority 1 groups are on the same side, the stereochemistry is Z here for this Wittig reagent that has no electron withdrawing groups. However, for Wittig reagents that do have electron withdrawing groups, such as ester groups here, attached 1 carbon away from the carbon phosphorus double bond, or a benzyl carbon, 1 carbon away here from the benzene ring. In those cases, we'll have a E product form. So if we look here, we can see that again, the carbon here beats the hydrogen priority, the carbon here beats the hydrogen. So our priority 1 groups are not on the same side, they're on opposite sides. So that's E, not Z. And likewise here with this phenyl group that is electron withdrawing, we will have this priority 1 carbon here beating number 2 hydrogen, priority 1 carbon beating number 2 hydrogen. These 2 groups are on opposite sides, so it's E rather than Z on this double bond here. But if the Wittig reagent here contains an electron withdrawing group, we get the E alkene formed, as I just meant. An electron withdrawing group or a phenyl ring, it just delocalizes the anionic charge of the Wittig reagent, and that stabilizes it. Because remember, the Wittig reagent, when we're drawing it, we have a lone pair on the carbon. That carbanion, that's not a particularly stable situation. And so if we have that, this carbonyl that is allylic basically to this lone pair, we'll have significant resonance here, and that will stabilize this Wittig reagent. And likewise here, if we have an ester group, here we have, or here's the resonantly stabilized one, because we can also describe this. What's the HWE reagent is an even greater resonance stabilization because we have the resonance stabilization through the phosphorus and also through the carbonyl group here. So this is an alternative to the Wittig reagent. It's called the Horner-Wadsworth-Emmons reagent, or the HWE reagent. And it's similar to this resonantly stabilized Wittig reagent, but it's even further resonance stabilized, and it also will yield the E product as the result here. So for example, here's the HWE reagent. Again, we have a similar mechanism where we're going to have the nucleophilic attack on the oxygen, and we're going to have a subsequent formation of the bond and then an ultimate loss of a stabilized product. But what ultimately happens is with the HWE reaction is we have the ejection of that phosphorus containing group, and we essentially have the installation of this entire group, and where there was a double bond to the oxygen, there's now a double bond to this carbon. So this carbon right here is double bonded here, and then we have the whole rest of the group attached right there. So there's lots of factors here. The choice of the solvent and the use of Lewis acids can affect the stereoselectivity. In terms of the mechanism for this part, the exact mechanism, this will be stated in the book a little bit later, in chapter 20, I believe. So for Wittig and these HWE reactions, it's important to note that when we make this double bond, this could be made with two potential Wittig reagents. So for example, here, if we have on this secondary carbon a double bond to a primary carbon here that's involved in the double bond, what we could have is we could have a Wittig reagent, this ketone, and a Wittig reagent that contains one carbon. This would be, if we do this arrow, we have this negative formal charge here. We can see that it can do a nucleophilic attack on this one, and then we have that cyclic 2,2 cycloaddition, and then we have the ejection of that phosphorus containing the triphenyl triphenylphosphine group. That's what they call it. So the ejection of the triphenylphosphine group, and ultimately we get a bond between this carbon right here and this carbon right here, right? They're going to be a bond. It's going to replace this oxygen atom. And so that's basically this product right here, this carbon and this carbon. Alternatively, we could have this carbon here being the negative carbon right here, if we draw it this way. So this is negative, this carbon right here, and we can have the nucleophilic attack of, whoops, cancel my pen here. And we can have the nucleophilic attack of this guy on the carbonyl, and of course this mechanism continues, but that's a key first step. It also involves the formation of this sigma bond between the oxygen and the phosphorus, and then the decomposition, of course. But the ultimate result would be that we have a bond between this carbon right here and this carbon right here, which would be these two carbons again. Here having that whole butyl group, and here just having the two hydrogens. And so the question is, synthetically, of the two possible routes, which one would you want to choose? And the decision that you make has everything to do with how easy it is to form the Wittig reagent. So recall from earlier that when we formed the Wittig reagent, it involved the nucleophilic attack here of this phosphorus lone pair on a primary alkyl halide, or in this case, a methyl alkyl halide. And so since this is an SN2 reaction, the less substituted the carbon is, the easier this is going to be to create that Wittig reagent. So going back to our selection of Wittig reagents, if we look here, this Wittig reagent would be formed from a methyl bromide, as we saw in that previous example, and would be much easier to form. However, this Wittig reagent here would require a 2-bromobutane, which is secondary, and thus the SN2 reaction would not be as good. And so the Wittig reagent with the carbon that's less substituted here is more likely to be formed. So for route 1, again, we needed the methyl halide for our SN2 reaction, and it involves a nucleophilic attack and then the breaking of this bond. So there's a lot less steric hindrance here involved in the formation of this Wittig reagent. However, this is a secondary alkyl halide, and so we're going to have a much slower SN2 reaction due to the steric hindrance. And so route 1 would be better, since the SN2 reaction needed to create the Wittig reagent. The Wittig reagent here would be much faster than the secondary, using the secondary alkyl halide here to create the alternative Wittig reagent. So when we're thinking about synthesis, when we analyze this in reverse, we think about the two possible routes to create the alkene using the Wittig reaction, and we would want to use the 2-butanone here as the ketone, and this Wittig reagent here, again, this being the negative, for the nucleophilic attack, just because this was a lot easier to produce, given that it would only require a methyl halide here. Now, an oxidation that we're going to consider here that will alter the structure here or produce a new functional group from a carbonyl is the so-called Baeyer-Villiger oxidation. And in this oxidation, essentially what happens is an oxygen atom is inserted between the carbon atom and the carbonyl and another carbon atom. And so an aldehyde or a ketone will be converted to an ester, an aldehyde will be converted to a carboxylic acid. The way this goes in terms of mechanism is, again, we're following the same pattern as every mechanism we've seen in this chapter, is that there's going to be a nucleophilic attack that's going to occur on the carbon in the carbonyl. And in this case, if we're using a peroxy acid here, which has a structure like this, remember it's abbreviated RCO3H because it's R, which is whatever this is the R, and then C, here's the C, O3, and then we have 1, 2, 3 oxygens, and then H for this hydrogen here on the second oxygen. So what we're going to have is a nucleophilic attack by the oxygen on the carbonyl, and our resonance arrow showing the lone pair here going up onto the oxygen, giving it 3 lone pairs and 1 bond for a -1 formal charge. And then we have a movement of this proton. Now this oxygen now has only 1 lone pair remaining. It gave up 1 lone pair to create the sigma bond to the carbon. So it has 3 bonds and 1 lone pair, giving a positive formal charge. If this proton is moved over here, so we can have a transfer of this proton. So this lone pair here on this oxygen is going to do a proton transfer, and then these 2 electrons will be left behind, giving this oxygen now 2 bonds once again and 2 lone pairs, giving it a 0 formal charge. At that point, we have a final cleavage here of this last bond right here. And so we have the resonance arrow again putting these electrons back down to this carbon, which it can do. It will give it 4 bonds because there will be a cleavage between this carbon and this carbon bond, ultimately putting an electron pair here on this oxygen. Meanwhile, this sigma bond is going to break, and this carbon already has 4 bonds, so we should also write a resonance arrow here to show that this lone pair now resides on this oxygen. And at that point, we have this this rearrangement essentially. We have a carbon-oxygen double bond right here, and we have this R group attached to this oxygen. So this R group right here, this is the one that moved over to this oxygen, so it's right here now. We now have not a lone pair here, we have a double bond between this carbon and this oxygen. We had a breakage of this bond right here, and so it's no longer there, but we're going to have now a double bond between this carbon and this oxygen. So we have this oxygen here now making a double bond with this carbon, and now the movement of these electrons here makes a single bond between this carbon and this oxygen. And now this oxygen will once again have two lone pairs and 2 bonds, giving it 0 formal charge. And this R group, the group we're calling R there, whatever it is, it can, in this case, it's a methyl group. This R group, wanted to give it a purple color here. This R group, that's this one right here, and that is still there. It's right here, it's right here, and it's still there. It's right here, but it's no longer a part of the main molecule here, that our reagent molecule that we were concerned with. That is now an ester. It is essentially inserted an oxygen atom between between this carbon and this carbon. So this R group here moved over. If you have a cyclic ketone, this is also going to produce an ester, but in the cyclic fashion here. So we're going to still have the same number of carbons, 1, 2, 3, 4, 5, but now we're going to have another atom, an oxygen atom in here. And so this is going to become a cyclic ester. And for each of these reactions, we have to think about here, what is going to be migrating over here and attaching itself to the oxygen, okay? And in terms of, because there's multiple possibilities, right? We have a couple of R groups here. The question is, which is going to move over and attach itself to the oxygen? And to decide that, we're going to base this on this pattern here, is that hydrogens will be the easiest to move over. And the way I remember that is that hydride shifts are very easy. For example, hydrogen atoms moving over is in close proximity like that is not as difficult. And then we have a pattern here that's related to stabilizing any potential positive charge in the transition state here, which goes best on tertiary or a phenyl group here, followed by primary and methyl being lowest rate of migration here. So for example, what this means is that, let's say you're deciding what's going to happen here when you when we have the production of the ester from this ketone right here. Is the oxygen going to position itself between this carbon and this one right here, or is it going to position itself between this carbon and this one right here? And if we're looking at this trend here, we have this tertiary carbon, and so that's high up here as opposed to a primary carbon. And so the oxygen is going to end up being positioned between the tertiary carbon here and the carbonyl carbon, not the primary carbon and the carbonyl carbon. However, if we do this with this benzyl here on one side and the hydrogen on the other, well, the phenyl group here is lower in priority than the hydrogen. The hydrogen is going to be the one that ends up being on the other side of the oxygen in this reaction. So when it comes to deciding on synthesis problems, so as we continue, we've now done another chapter where we're adding even more reactions to our toolbox. And we want to keep reminding ourselves when we do synthesis problems what is the difference? What are the key differences between our starting reagent and the molecule that we're trying to produce? The first thing you're going to want to look for is changes in the carbon skeleton, because those are really, really big tips of which reactions are going to be involved in your synthesis. We've had a couple of ways to change the carbon skeleton. One was reaction with alkylnide ions, right? That was one. That can add on, and this would be R, that can add on a carbon in this case with a triple bond, and then we can go on and do other things with that. We also saw the Grignard, R basically, where ultimately the R is going to be a is going to be having negative formal charge, be a carbanion. And then subsequent treatment with sodium hydroxide, hydrogen peroxide, sodium hydroxide, rather. Whoops, going back here. Subsequent treatment with a means of protonation. Sorry, where is it? I'm trying to go back to Grignard here. Subsequent treatment with a means of protonation for the oxide here. And then finally, we have now a new reaction. We have the Wittig reagents. The Wittig reagents where we have some phosphorus group, an R group here, and it's a triphenyl phosphorus. And really what this represents is another kind of negatively charged right here. So we show this, and then we have, oops, like that. The negatively charged R group here and a positively charged phenyl group when we take this and instead make it a lone pair. So all of these come from these kinds of nucleophilic substitutions. In this case, if we're looking for a product that ultimately has a carbon-carbon double bond, we'd want to use the Wittig reagent. If we're looking for a added carbon with an alcohol group, we'd use our Grignard reagent. If we want to produce a cyano compound, we'd use the KCN here. And finally, again, if we were trying to use make the carbon-carbon double bond, we'd use the Wittig reagent. And these are all the three ways that we have to expand on, or rather four, I guess, if we can include this cyano one. These four ways to change its carbon skeleton, or at least to add to it. We have one way of making it smaller. That would be the ozonolysis. So that really narrows down, thinking about this question really narrows down which reactions we have to consider as a part of our synthesis, and can help to get us started in figuring out the whole thing. We should also think, is there a change in the functional group? So we've had many, many different ways to change functional groups. For example, reducing alkynes to alkenes and to alkanes. We've had here reducing carbonyls to alkanes in this chapter. In previous chapters, we've also had addition reactions, hydration, dehydration reactions, particularly if we're looking at chapters 7 and 8. It does give us a lot of different types of reactions there that change the functional groups. So for example here, we have ways to change all of these functional groups, right? We've learned these in the past, and at this point, these really need to be like committed into your memory here. You really need to be able to kind of, whoops, where did I switch slides here? Right here. Oh no, I went all the way back. Where's my slide? So you really need to be aware of all these different ways and be able to fill in a chart like this from your memory, because once we get to the ACS exam, you'll no longer have these, all of these. So for example, if you're going from triple bonds to double bonds to single bonds, first of all, the important thing to remember is that alkanes are fabulously unreactive. There's very little that you can do to make them react. The way you start to make them to react is you functionalize them, right? And so you can functionalize them by adding a halogen atom to them. And that's often the way you want to start a reaction if you're just starting with an alkane. That's a key idea in synthesis. Also, if you want to make a double bond, well, you're going to start by functionalizing it, right? And then after that, you're going to do you'll do an elimination. And so you'll treat with a strong base of some kind. So I'll just say base. It could be sodium ethoxide, sodium methoxide. It depends on how it is. How it could be terbutoxide. Depends on regiochemistry considerations. If you want to reduce the alkene to the alkane, it's H2 and platinum. Um, that's all you need. Now it's a little bit more complicated when you want to reduce the alkyne to the alkene. You have to be careful not to reduce it all the way. If you use H2 and platinum, H2 and platinum will get you all the way from uh, alkyne all the way to alkane. So if you want to go from alkyne to alkene, you have two methods. If you want to do a syn addition, you can use the H2 Lindlar, which is a poison catalyst. If you want to do an anti-addition, you can use the dissolved metal reduction with the sodium. And so that's and sorry, the solvent here, the NH solvent and reactant, the ammonia. So, and then if you want to do a double, if you want to make the alkene into an alkyne, you have to again make something so you can do a super addition here. You'll do, for example, Br2 adding bromine, and often the solvent is mentioned as CCl4, but you don't necessarily have to mention that. Then you'd need something super acidic to do a double elimination, which would be the NaNH2 with the and then with NH3, and then finally, this is people like 1, 2, 3. You'd have a protonation here just simply using water. Now, if you want to make an a halogenated alkane from an alkene, you'd simply do an addition reaction. You can use HX, for example, or you can use HBr and ROR. If you want to do an anti-Markovnikov addition where the halogen atom adds to the less substituted carbon, depends on your regiochemistry considerations there. And again, if you want to do if you want to make the alkene just like we saw here, after you've halogenated it, you would want to use a base of some kind. And your choice of bases here could be the non-sterically hindered bases like sodium hydroxide, sodium ethoxide, sodium methoxide. Or you can use a sterically hindered base, which is usually written as TBU, TBUOK. You could also use bases that are like DBN or DBU that are not nucleophiles if necessary. So these are all options for bases, and these would all be acceptable. If you're trying to hydrate here, there's a number of different ways that you can hydrate. If you're doing a dehydration, you'll generally use, just to write down here, concentrated H2SO4. If you're doing a hydration, there's lots of ways to do hydrations here. We can simply use an acid. We can use dilute H2SO4 and water, or just some kind of acid. That would work for hydrating it, acid and water. And also we have a number of other ways of hydrating. We have the oxymercuration, demercuration here. We have so let's do this one. We have the hydroboration oxidation. If you want to add the OH group in the less substituted position, which is BH3THF, which is a solvent that stabilizes it. And then step 2, we react it with hydrogen peroxide and sodium hydroxide. So that's another way of doing it, to add it in a non-Markovnikov way. Or we can have the oxymercuration demercuration, which would add in the Markovnikov way and avoid carbocation rearrangements in the case that is something that you have to worry about. And that would involve step one, the mercuric acetate reagent. And so we'd have HgOAC2, and then subsequent treatment with sodium borohydride to as a source of the hydrogen atom and sodium hydroxide. That's step two. So we have several ways to hydrate depending on what kind of regiochemistry that we want. If we want to oxidize the alcohol to a carbonyl, we could use PCC, a soft oxidizing agent, so that we don't oxidize if it's an aldehyde. If we use a strong oxidizing agent such as chromic acid, HCr2 or CrO4, or you can use sodium dichromate with acid, which essentially is the same thing, Cr2O7. This will be the hard oxidation, or the and this would produce in an aldehyde a carboxylic acid. So usually what you want to do is go with the soft oxidation like PCC. When it comes to reduction, again, we can have a hard reduction reagents or soft. If you use like lithium aluminum hydride followed by water here afterwards, that can reduce your alcohol. From there, we have all of the reactions that are covered in this chapter, which I'll review at the end, but those are all reactions that you can act on a carbonyl. And so we're starting to create this big network of reactions that I think it's really useful for you to go through and reproduce a diagram like this for yourself so that you can follow that pathway through and determine where you're getting at with your synthesis. And filling in, like basically going back to this slide, filling it in all yourself, and then filling the reactions that I'm going to show you at the end here is a really good way to kind of practice and get that in your head. Of course, doing synthesis problems after that is the real way to get good at synthesis problems. So you'll notice that for the homework for this chapter, I assigned problem number 40, which is a series of synthesis problems, which will really help you to get these reactions in your mind and understand how to get from point A to point B in a synthesis. When it comes to spectroscopy, we talked about this in chapter 14, but here's a little bit additional information. In terms of carbonyls, you know you're going to find their IR stretches at around a little over 1700. However, if you have some resonance to them, that's going to delocalize the electrons and result in a little bit lower here difference in energy for the vibrational energies, and thus a lower wave number absorption. If we have a cyclic carbonyl, the ring strain will affect the energy here of the absorption, the vibrational energy. The more restrictive the cyclic arrangement is, the larger the wave number. And in addition, watch out for the aldehyde CH stretch. So these are all carbonyl ketones, but if you have an aldehyde, this CH stretch occurs somewhere around 2700 to 2800 wave numbers. And so that's a really good giveaway for an aldehyde, particularly if it's confirmed in an NMR. And so here's a picture of that aldehyde CH stretch occurring about 2719 for the aldehyde. In addition, we get the carbonyl stretch, C double bond O, at around 1750-ish. And so this combination of factors here is enough to usually identify the aldehyde on a molecule by the IR alone. But if you have the NMR confirmation, there's also a dead giveaway on NMR. You're going to have a very, very downshifted here, a very, very high ppm peak usually, and it's going to be a singlet because there's no hydrogen atoms attached. So on the hydrogen NMR, you get this this singlet over here around 10 ppm, and so that really, really indicates for you the presence of an aldehyde. In addition, it's important to remember that the protons next to a carbonyl will be significantly de-shielded. And so you're going to notice that you'll get some hydride stretches on the carbon neighboring the carbonyl carbon in the 2 to 3-ish region rather than the normal low ones or 1.2 region here if there's no deshielding occurring. For the carbon NMR, the carbonyl proton is going to give you a very downshifted signal here as well at about 210-ish ppm, 200 ppm. And so the combination of all these spectra can really point out to you that you have a carbonyl. Finally, we talked about all the reactions that would be required that could be used to create a carbonyl. Once you have the carbonyl, we've learned in this chapter a whole host of reactions that can be done to turn that carbonyl into a variety of other functional groups. And so just in summary, if we react under acidic conditions, a carbonyl with water, we end up with this dihydroxycarbon here. If we treat in the presence of an alcohol, we will get an acetal like this. In the case of a diol, we'll get this cyclic acetal here. In the case of a diethiol, we'll get the cyclic thioacetal here, which can be subsequently reduced by Raney nickel to reduce it all the way to an alkane. And so notice these pathways too. These pathways can be used to get rid of the carbonyl bond and eliminate it completely. The other option here being to use the hydrazine here and get this imine-like product here, and then subsequently reducing with sodium hydroxide and water to produce the alkane with no carbonyl group. If we're treating, when it comes to using nitrogen as a nucleophile, if we treat with a primary amine, we're going to get what's known as an imine, meaning a carbon double bond to nitrogen. However, if we treat with a secondary amine, we're going to get this enamine, where we have a double bond between the carbon and the neighboring carbon and a single bond between the nitrogens. If we treat with NH2OH here, the nitrogen will perform as a nucleophile attacking, and we'll have the OH group still there. Finally, we can, and these are reactions we've learned previously in the alcohol chapters. All of these are old. These two are old reactions here. Reduce the carbonyl with lithium aluminum hydride, followed by acid to protonate the alkoxide ion that gets produced as an intermediate to get you the alcohol. If you use a Grignard reagent, you're going to get an alcohol from the carbonyl, but also add carbon atoms, however many carbon atoms are on this chain. And if we use potassium cyanide in an acidic environment, we'll get this cyanohydrin. If we use a Wittig reagent, we'll get a carbon-carbon double bond. And finally, if we use a peroxy acid, we will get an ester from the carbonyl. And the oxygen atom will be positioned in a way that is dictated by those priority rules we said, hydrogen and then tertiary phenyl and so forth. And so that concludes this chapter. Again, I encourage you to practice with the homework that we started with, but at the very end, make sure to hit problem number 40 with synthesis reactions. I think that doing some synthesis reactions is really helpful for review and also really drives these new reactions home in your head. I hope that all goes well, and I'll see you in the next week's lectures. Have a great weekend. Bye-bye.